Welcome back to CSConnect series. Under number systems, we also have an additional topic called data representation. How do you represent data using these number systems? We may not use all number systems together, but we may rely more on decimal and binary numbers. This video is dedicated to binary codes. We will have a look on various binary codes that are used. We have seen this flowchart already in digital electronics introduction video. The electronic digital systems usually have two kinds of signals. One signal is the low signal, which is represented by 0, and the other one is high signal, which is represented by 1. Electronic digital system has certain circuit elements. Those circuit elements represent the two signals as two states. One state is called the on state and other state is called the off state. On state is represented by 1 and off state is represented by 0. Binary signals are involved in electronic digital systems. When we take the circuit elements, binary elements are involving. What are these 1 and 0? They are the binary digits. When we say 0, it means it is a low signal as well as off state. When I say 1, it is on state and a high signal. So based on the kind, whether it's a digital system which is represented by signal or the circuit that is represented by the state, there are only two digits involved and they are called binary digits. From the term binary digit, we derive the word bit. Binary digit is what we call as bit. Now let's have a look about the binary digits. When we say there is one bit, that is when we say there is one binary digit, this digit can either be 0 or 1. Here when there is one bit, there are two possible values. When we take two bits, let's take 0 and 1 from the first bit. What will be the second bit? From 0, I have a possibility of 0 and 1, and from 1, I have a possibility of 0 and 1. We can represent this as 0, 0, 0, 1, 1, 0, 1, 1. This is how we can represent it. So while representing, this particular branch will give rise to 0, 0. This particular branch will give rise to 0, 1. This branch will give rise to 1, 0. And this branch will give rise to 1, 1. So when there are two bits involved, 4 possible values can be taken out. What about 3 bits? So let's take the first bit 0, 1. So this is the first bit representation and this is the second bit representation. So under 0, I have 0 and 1. Under 1, I have 0 and 1. Now this is the first bit in 3 bit. Let's take the second bit which has 0 and 1. So in this the possibility will be 0, 0, 0, 1. Then here it will be 1, 0, 1, 1. Now we have a third branching where each of the zeros and ones will have 0 and 1 again. So let's take 0 and 1 here. So this will result in 000 for this branching and 001 for this branching. So the first two zeros will remain as it is. The third bit will have 0 in one case and 1 in the other case. Similarly, the next branching, we'll have 0, 1 steady here and the third bit will have 0 here and the third bit will have 1 here. Similarly, we have 2 branching here. So 1, 0 will be steady. It will be accompanied by 0th bit here and it will be accompanied by 1 bit here. Again we have 2 branching. Along with this 1, 1 we have a 0 and along with this 1, 1 we have a 1. This is how we form 3-bit binary digits. Now the digits will be 0, 0, 0, 0, 0, 1, 0, 1, 0 and 0, 1, 1. All these 4 digits belong to this 0 part. So it is starting with 0. Since the second bit is 0 here, it will have 2 zeros here. Since the second bit has 1 here, it has 1s here. And the third bit has 0 and 1, it is 0 and 1. Similarly, the third bit has 0 and 1. Now let's take the right branch. We have starting bit as 1. So every bit starts here with 1. Then we have 0 for 2 branches and 1 for 2 branches. So this is 0, 0, 1, 1. And the third bit, we have 0, 1 in alternate position. So 0, 1 for this branch and 0, 1 for this branch. From here we can understand when there are n bits, there are 2 power n elements possible. When n is equal to 1, we have 2 power 1, 2 elements, that is 0 and 1. When n is equal to 2, we have 2 power 2 elements, which is equal to 4. We have 4 elements. When n is equal to 3, we have 2 power 3 elements, which is equal to 8. So there are 8 elements. N bits are arranged in 2 power n distinct ways. There are only 2 digits involved here, 0 and 1. But in how many ways they are arranged? They are arranged in 2 power n ways. So here they are arranged in 2 ways. One as the 0 and the other as the 1. Here they are arranged in 4 ways. 0, 0, 0, 1, 1, 0, 1, 1. Here they are arranged in 8 ways, as we see below. N bit code is equal to 0 to 2 power n minus 1. What is 2 power 1 minus 1? It is 2 minus 1, which is equal to 1. So they say it is from 0 to 1. So we have 0 and 1 here. When we take 2 power 2 minus 1, it is 4 minus 1, which is equal to 3. So the range will be from 0 to 3, which means 0, 1, 2, 3. 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. Then we go for 2 power 3 minus 1, which is equal to 8 minus 1, that is equal to 7. So here you can see 0, 1, 2, 3, 4, 5, 6, 7. So this is what they have represented in general as 0 to 2 power n minus 1. Now we will learn about decimal codes. Numbers representation in digital computers happen in 2 ways. One is binary and another one is in decimal format. Both these representation are done through binary code. If a person enters some decimal form information, they are stored internally as decimal code and not the exact decimal form. Each decimal digit requires a minimum of 4 bits. That is n is equal to 4. Till n is equal to 3, we saw the branching there. Why do they require 4 bits? Let's take 0 to 9 here. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. 7 we require 3 ones and 0 3 zeros. For 8 the representation will be 1,000 and for 9 the representation will be 1,001. So how many bits do you need to represent 8 and 9? We need 4 bits. So when you take decimal digit, they belong to 0 to 9 range. Even though you can represent 0 to 7 in 3 bits, you need the 4th bit to represent 8 and 9. That's what they have given. Each decimal digit requires a minimum of 4 bits. When there are 4 bits, you can easily represent them from 0 to 9. For arithmetic operations, decimal numbers are converted to binary and then they are done. In the previous videos, we saw about converting decimal to binary. And here they have mentioned something as binary code. Binary conversion, binary code. Are they same? Let's see the difference. Conversion of decimal to binary versus binary coding of decimal number. You could have seen a video called conversions where we converted decimal to binary, octal, hexadecimal, then we converted binary to decimal, octal, hexadecimal and all. That conversions part is this part. Binary coding of a decimal number is what we are going to see in this video. What is the difference? Both the content will have a series of bits. Bits means binary digits. After converting decimal to binary, you will have a series of bits. In the same way, the binary code will also have a series of bits. So in both the cases, bits are involved. Here the bits are the binary digits. Here the bits are combinations of ones and zeros arranged as per rules of code. This is the major difference. During conversion, decimal number 13 is equal to 1101. So let's check 13 divided by 2. 2 6 are 12, the remainder is 1. 2 3s are 6, the remainder is 0. 2 1s are 2, the remainder is 1. Just write it in reverse, it is 1 1 0 1. So even when you write it in the form of 8421, this will be 1101, which is equal to 13. This is the binary value of decimal value 13. Here we are converting into binary number where binary digits are involved. What about the bits in binary coding? So this 1 3 is 13 here together, but here it is 1 and 3. So let's have 0, 1, 2, 3. Let's take the 4-bit representation. 8, 4, 2, 1. How do you represent 0? 0, 0, 0, 0. 1 will be represented as 0, 0, 0, 1. 2 will be represented as 0, 0, 1, 0. 3 will be represented as 0, 0, 1, 1. For 13, you used the 8421 code to get the binary equivalent, or you used the division by 2 to get the binary equivalent. But here the number will not be read as 13. Instead it will be separated as 1 and 3. What is the binary code for 1? It is 0, 0, 0, 1 from here. And what is the code for 3? It is 0, 0, 1, 1. Now separate this and see. So let me write 1, 3. This is 0001 and this is 0011. So far we have been seeing how to represent numbers, but along with numbers we also have other characters that the system needs to represent. So for that purpose we are going to use binary coding. We will first start with binary coded decimal. It's a straight assignment of the binary equivalent. This is called weighted code. So let's take the decimal number 0 to 9 and let's find out the equivalent binary code. So we are going to use straight assignment, which is 2 power 0, 2 power 1, 2 power 2 and 2 power 3. Here they say something as weighted code. Where is the weight? The values are the weight. Why do they say as weight is when you assign 1 to a particular column. Say for example, if I assign 1 here and the zeros everywhere, when you multiply 1 into the weight, I get the value 4. So this is how 4 is represented. When I have 1 and 1 here, 0 in 4 and 1's place, how will we get the value? 1 into 8 plus 1 into 2. This gives 8 plus 2, which is equal to 10. When you are multiplying the value by the weight and summing them up together and you get a value, that comes under weighted code. Here 8, 4, 2, 1 are the weights. So when you multiply the binary digit or the bit with the weight, you end up with the number that you want. So how do we represent decimal in terms of BCD? So let's take the decimal digits in the side. 8 plus 4 plus 2 plus 1 will totally give you 15. Now how will you get 0? When I assign 0 in all the places, this becomes 0. What about 1? I have to place 1 only in the 1's place. Remaining place will be taken as 0. How will I represent 2? I have to represent 1 only in the 2's place. The remaining places will be 0. This is actually similar to converting decimal to binary because this is given as a straight assignment of the binary equivalent. Though they say it's a weighted code, we have formed the weights only with 2 power 0, 2 power 1, 2 power 2 and 2 power 3. What about 3? 2 plus 1 is equal to 3. So we are mentioning 1 in 2 and 1. The remaining places are 0. What about 4? I will place 1 under 4 and 8, 2 and 1 will have 0. How will I represent 5? 4 plus 1 is equal to 5. The remaining places are 0. What about 6? 4 plus 2 is 6. The remaining places are 0. What about 7? 4 plus 2 plus 1 is 7. The first bit is going to be 0. What about 8? 1 will be present for 8. Zeros are present everywhere else. What about 9? 8 plus 1 is 9. The remaining places are 0. So this is the binary coded decimal for the decimal digits. This is the BCD part. The next code that we are going to see is XS3 code. XS3 code is nothing but it is BCD plus 3. You have to move 3 positions from the BCD code. So where are these XS3 code used? XS3 code is the decimal code that is used in old computers. Why do they say it as decimal code? Because you are representing the decimal number in decimal code. Instead of the decimal number, it has these many codes. We call them as unweighted code because you are not relying on the weights 8421. You are just moving 3 positions from 8421 code. So this is an unweighted code. When you form directly from a particular weight, you call them as weighted code. When you don't rely on weights, it becomes unweighted code. So how do we find XS3 code? By BCD plus 3. Let's take 0 to 9. If it is 0, I have to move 3 digits later. So 0 plus 3 is equal to 3. What is 3 in binary? It is 0011. So this will be the first digit. What is 1? 1 plus 3 is equal to 4. So here we have to write 3, 4, 5, 6, 7, 8, 9. Then we have 10, 11 and 12. So what are these 10, 11 and 12? They are from the 8421 code, which is the BCD. So let's start with 1 now. So we need to represent 4. So 4 is 0100. Then we have 5. 0101, then 6, 0110. 7 is represented as 0111. 8 is represented as 1000. 9 is represented as 1001. How do we write 10, 11, 12? So we have a short table here. 8 plus 2 is 10. So we have zeros in 4's and 1's place. 11 is 8 plus 2 plus 1. 8 plus 2 is 10, 10 plus 1 is 11, so this is 0. What about 12? 8 plus 4 is 12, so I am placing 1 here, the remaining 2 places are 0. Now, 7, 8, 9 are taking values from 10, 11, 12. It is because 7 plus 3 is equal to 10, 8 plus 3 is equal to 11, 9 plus 3 is equal to 12. What about 7 now? We have to write 10's value. So, 10, 10. The value 11 will be 1011 and 12 will be 1100. So this is the XS3 code. After XS3 code, we are moving to another weighted code. The name itself is written as 84 minus 2 minus 1 code. What is this code? It assigns negative weights to decimal code. So how many digits can be formed? When I add 8 plus 4 plus 2 plus 1, you can form till 15 value in decimal. When it is 8 plus 4 minus 2 minus 1, you can form only up to 9 digits. So we can accommodate from 0 to 9 definitely. Let's take the decimal digit 0. When will you get 0? When all the places have 0, it is 0. There is no change. When will you get 1? You have 4 here. 4 minus 2 is 2. 2 minus 1 is equal to 1. We have to mark 3 ones here and a 0 here. So let me explain you here. The weight is 4. I have 1 plus weight is minus 2. I have 1 plus weight is minus 1. I have 1. And here the first weight is actually 8, but I have a 0 here. 0 into anything is 0 plus 4 into 1 is 4. Minus 2 into 1 is minus 2. Minus 1 into 1 is minus 1. This will give 4 minus 3, which is equal to 1. Did I get 1 here? How did I get this? By multiplying it with the weights. So this is also a weighted code, but this code assigns negative values. Whenever we multiply the ones position with a particular weight, it comes under weighted code. Now let's form 2. So we have only minus 2 here. In what way we can get 2? If it is 4 minus 2, we can get 2. So under 4 and minus 2, I place 1 and the other 2 places are 0. So only when you understand how to do this, you will be able to do for any other code. Now for 3. How can I get 3? When I add 4 and minus 1, I get 3. So under 4 and under minus 1, I place a 1. The other 2 places are 0. How do I get 4? I can have 1 in the 4th place. The rest are zeros. How do I get 5? I can take 8 minus 2 minus 1 which is equal to 5. So here 8 minus 2 is equal to 6. 6 minus 1 is equal to 5. So how many places should I give 1? In 8, in minus 2 and minus 1, I can have 1s. 4 will have 0 here. What about 6? 8 minus 2 will give 6. So under 8 and under minus 2. The rest of the places will have 0. How about 7? 8 minus 1 is equal to 7. So let me write this as 8 minus 2 is equal to 6. So 8 and minus 1 will give 7. These two numbers will have 0. What about 8? 1 under 8 and the rest are zeros. How about 9? You have 8 plus 4 which is equal to 12. Then you have minus 2 and minus 1 which makes minus 3 which is equal to 9. It means when you have 1 everywhere, it becomes 9. So this is what we calculated in the starting. So now we have got 8, 4, minus 2, minus 1 code. Next we will move to 2, 4, 2, 1 code. It's a weighted code and let's see how to do them. So what is 2 plus 4 plus 2 plus 1? It gives 9. So you can represent from 0 to 9. Let's take 0 first. We'll have zeros everywhere. I'll start with 9. 2 plus 4 plus 2 plus 1 will give you 9. So I'll give 1 everywhere. Now let's go for 1. Only under 1 I will have 1. The rest of the places will be 0. What about 2? I can place 1 here and the remaining places as 0, or I can even place this as 1 triple 0. The starting number is also 2. So either this or this. We'll stick to this as of now. I'll tell you what are these afterwards. What about 3? So this can be 2 plus 1 which is equal to 3, or 2 plus 1 which is equal to 3. What about 4? 0, 1, 0, 0, or 2 plus 2 can be made 4 in the other way also. There is also another possibility I am saying, but this is what we are sticking to. Generally in this form what we can do is, we have 10 numbers totally. We have given 5 zeros in the starting. So we will make sure the next 5 will be starting with 1. Now how will you calculate for 5? You have 2 here. 2 plus 1 will give you 5. 4 plus 1 can also be 5. So it can be 0, 1, 0, 1 also. And next for 6. If this is going to be 2, then I can mark 4 as 1 so that it becomes 6 with 2 plus 4. The remaining 2 places can be 0. And the other way of doing this is, I can make 4 and 2 as 1 and the first and the last one as 0 also. This is actually 101, 110 which is following BCD code. We are not going with this way. Instead we are going with a different strategy of first 5 rows with bit 0 in the starting place and last 5 rows with bit 1 in the starting place. Then what about 7? We have 2 plus 4 plus 1 for 7. 2 plus 4 plus 1. Then for 8 it is 2 plus 4 plus 2 with a 0. For 8 and all you don't have any other representation, because only when you add the first 3 digits 2 plus 4 plus 2 you will get 8. For 7 at least you can have this binary coded decimal, but we are not getting into this way. So we are not moving into this part. We are concerned only with this table. So let's see the 2421 code. You can see here the first 5 rows have 0 in the first bit and the last 5 rows have 1 in the first bit. Similarly, it is there for 84 minus 2 minus 1 and 2421. So in order to follow this pattern, I have chosen this. In case they ask you, what is the other way you can represent this 2421 code? At that time, you can go with this manipulation. So you can ask me, certain numbers have values from 10 to 15. Say for example, this is having only 9 numbers. This is having only 9 numbers in the extreme. So 8 plus 4 plus minus 2 plus minus 1 will give you 9. 2 plus 4 plus 2 plus 1 will also give you 9. Here this BCD code will go till decimal value 15. Usually decimal value 10 to 15 are called as unused bit combinations, because in binary coding from 10 it is split as 1 and 0. That's why we are considering digits only from 0 to 9. You can take digital design or digital electronics book. You will find 0 to 9 here. They would have given a line from 10 to 15. Certain codes will be filled and they would mention it totally as unused bit combinations. In binary code format, the number will be split into two because we are learning binary codes for representing information. That's why we don't go with the decimal values 10 to 15. The next code is reflected code. Digital system processes data in discrete form. If you take any physical system, it would keep supplying continuous output data. And these data will be converted to digital or discrete form. If it is discrete, it is digital, or if it is digital, we can say it's discrete because digital systems are going to operate on discrete elements. So this digital data is applied to the digital system. So when we have value from physical system to digital system, we always have a conversion of continuous data to discrete data. What is continuous data otherwise called? It is analog form of data, and this discrete form of data is the digital data. So in order to convert this analog to digital, we will be having an analog to digital converter. This converter uses a code called reflected code. Now you can understand where this reflected code comes in. What about this reflected code? Why they are here? These are the representation of digital data that are converted from analog data. What kind of code is this? The number changes by only one bit as it proceeds from one number to the next. So far we have seen codes like 8421, 2421. In that we have weights representing the values of the decimal number 0 to 9. But in reflected code, the value will be changing only by one bit. Say for example, if there are 4 bits, if this is 0 here, the next value will have the same set of values with 1 changing here. In case if this is going to be a 1, the next value will have only 0 in this place. The rest of the bits will be the same. When the change occurs by only one bit, when it goes from one number to the next number, that is actually reflected code. Reflected code can also be called as gray code. So when you write gray code from 0, you have to make sure that you change only one bit for the next bit combination. Now let's see the gray code. So we'll start with 0, 0, 0, 0. There are 4 bits. We'll start from the last bit and keep changing one by one. So first we'll make the change here. So the remaining places will stay as it is. Next we'll change this bit because if I change this again it will change to 0. So we will have 0, 0, 1, 1. Now we can change the final bit once again. So this is 0, 0, 1 and this becomes 0. What about 4? If I change the final bit, it becomes 2. So when I change 0010 to 0011, it is 2. So I cannot use that. When I want to change the third bit as 0000, it becomes 0. I cannot use it again. So the only option is I have to change the second bit. Now this bit is alone changed as 1 here. The rest of the bits will stay as it is. Now again I can start with the last bit. So let me keep these as it is and this one will be changed to 1. And now 0101. Now we don't have any combination here, so this can be taken. Let's change the last bit again. So this is also a combination that we did not get. If I change this bit, it will become a new code. After it, what I can do, I can again go to this bit 1101. The next code will be XS3 gray code. So from 3 we will be starting and we will need the gray code till 12. So here itself we will try to make from 10 to 15 so that we can use it for the next code. For 10 what we will do? From 9 I have 3 options. I can change the 4th bit first. 1100. It is already 8. Then I can change the third bit. This will give 4 ones. It has not been allocated so far, so we can use this. At the same time, when I change the second bit, it becomes 1001. This is also not used so far. If I change the first bit, it becomes 0101. It is already assigned to 6. So I cannot take these two codes. I can pick anything from these two. What I will do is I will pick the first one. I will make this as 1111. Again, I will start from the final bit. I'll make this as 0. Everything will be 1. I can change the third one, but it will represent 8 again. If I change the fourth one, it will become 10 again. My only option now will be changing the second bit to 0. The rest of the things can stay as it is. Now from here what I can do? Let me change this code. 1011. From here I can change it as 1001. So this option we are not using it here. Instead we can take 1011. Change the last bit, it is 1010. We have already gotten 12. Then we have 1001. This is not used so far. Then we have 4 numbers of 1. It is already used in 10, so we need not take them. Let's change the first bit 0011. This is already used in 2. So the only option available here is 1001. So let's take 1001. And now how can you change this? I can change the final bit again because so far I have not allocated this code. So let's list out the gray code here. Is this the only way to represent gray code? Not so. It is not mandatory that you have to start with the last bit. This is just one possible table of the gray code. If you take 4 zeros, I can start one even this way. Or I can start one even this way. All I need to see is between two consecutive numbers, only one bit has to be changed. The remaining 3-bit position should be same. That is the concept of gray code. To obtain a different reflected or gray code, start with any bit combination and proceed to obtain the next bit combination by changing only one bit from 0 to 1 or 1 to 0 in any desired random fashion. Make sure that no two numbers should have identical code assignments. So when I started from 9 to 10, I had two options, either to go with all 4 ones or 1001. So this is just one possible table of gray code. XS3 gray code. First we have to understand why gray code didn't work. There are two values 9 and 0 considered. 9 has a value 1101 and 0 has a value with 4 zeros. When you go from 8 to 9, only one bit has changed. After 9, when you get to 0, only one bit should change. But in fact, how many bits are changed here? Only one bit is staying the same. 3 bits have been changed. So gray code is not suited because the transition involves change of 3 bits. So this is actually breaking the rule of gray code. That's why we are going with XS3 gray code. So I have a set of gray code here. From here I should start with 3. So let's take 0. This should be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So obviously I will have 10, 11, 12 from our previous table. So let's take 3. 0, 0, 1, 0, 0, 1, 1, 0. 0 triple 1, 0 1 0 1, 0 1 0 0. For 8 it is 1 1 0 0. For 9 it is 1 1 0 1. For 10 we have 4 ones. For 11 it is 3 ones and 0. And for 12 it is 1 0 1 0. Now take 9. It is 1 0 1 0. Now take the first number 0. It is 0 0 1 0. How many bits are changed here? 0 1 0 is staying same and only one bit is changed. Does this follow the gray code rule? Yes, it is following. When we take 0 and 1, only one bit is differing. 1 and 2, only 1 is differing. 2 and 3, only 1 is differing. 3 and 4, 1 bit again. 4 and 5, 1 bit again. 5 and 6, it is 1 bit again. 6 and 7 has also only 1 bit differing. 7 and 8 has 1 bit differing again. 8 and 9 has 1 bit differing again. From 9 when I go to 0, it is 0 0 1 0 which is differing by 1 bit again. So this is satisfying that rule perfectly. So that's why they say gray code is not suited due to the transition from 9 to 0, but XS3 gray code is suiting because it follows the rule from 9 to 0 with change of only 1 bit. So these are the different types of codes. From this we will take a learning here. there are three weighted codes that are discussed. The BCD code, which is the 8421 code, the 84 minus 2 minus 1 code, and 2421 code. All these three codes are called weighted codes because we are multiplying the binary digit with weights and sum them to get the decimal number. Just pick this. 1011 1 into 8 plus 0 into 4 plus 1 into minus 2 plus 1 into minus 1. 8 plus 0 minus 2 minus 1. 8 minus 3 will give you 5. Is this 5? Yes, it is 5. How did we get this? By multiplying the binary digit with the weights and then summing them together to get the decimal number. You can randomly check with any value from these three columns that are highlighted. There are also codes called self-complementing codes. What are self-complementing codes? The 9th complement of a decimal number is obtained by changing the zeros to ones and ones to zeros. 9th complement is for decimal system. Changing zeros to ones or 1 to 0 is 1's complement. Why am I bringing both the things? What is the 9th complement of 0? 9 minus 0 will give you 9. Let's take the XS3 code. 0 has the value 0011. 9 has 1100. Is this the ones complement? Is this having zeros to ones and ones to 0? Yes. First two numbers are having 1 and last two numbers are having 0. It is a perfect complement. So that's why they are called self-complementing codes. Are only two values complemented? No. All the values will be complemented. 9 minus 0 is 9. So 0 and 9 are complements. Then we have 9 minus 1, which is equal to 8. It means 1 and 8 are complements. 9 minus 2 is equal to 7. 2 and 7 are complements. 9 minus 3 is equal to 6. 3 and 6 are complements. 9 minus 4 is equal to 5. 4 and 5 are complements. 9 minus 5 is equal to 4. So 5 and 4 are complements. 9 minus 6 is equal to 3. So 6 and 3 are complements. We can mention this way. 9 minus 7 is equal to 2. So 7 and 2 are complements. 9 minus 8 is equal to 1. So 8 and 1 are complements. 9 minus 9 is 0. So 9 and 0 are complements. 0, 9 or 9, 0 both are going to be same. Let's pick up 4 and 5. What is 4? 0, 111. Let's find the complement 100. Is this 5? Yes, it's 5. So in this case we pick up XS3 and 2421 as the self-complementing codes. We'll take 2 and 7 in 2421. So 2 is 0010. How do we get 7? 1101. Is this 7? Yes, it is there. So let's take the XS3 and 2421 codes. 0th row and the 9th row are the complements as mentioned here. Then we have 1 and 8 together. Then we have 2 and 7 together. We have 3 and 6 together. Then we have 4 and 5 together. So you can write the first 5 numbers and start finding the complements from the 5th number to the 1st number so that you will end up writing all the 10 numbers. So when they ask you is a particular code self-complementing or not, you have to write the codes and then check whether they are complementing each other. They give you a set of codes and ask you to find whether they are self-complementing or not. Find the decimal value of one code. Take the 9th complement. What is 9th complement? You have to subtract every digit from 9. When there are 3 digits like 1, 2, 3, you have to subtract it from 999. Since there are only 1 digit involved here, we are subtracting it from 9. The number that you are subtracting and the result together should be complementing. Here you are subtracting 0 and the answer is 9. So this way you have to find. They are useful when arithmetic operations are done in signed complement representation. What is this? This will be discussed later in this series. But to give a short intro, so far we have done arithmetic operations or subtraction using complements only with the positive numbers. We have not dealt with negative numbers. I am telling you m and n, the minuend, the subrahend, the addend and the augend, everything is positive. The answer may be positive or negative. That is not an issue. The operands are positive so far. But in signed complement representation, the number will be represented as plus something or minus something, and they will be asking you to do addition or subtraction. It will not be done immediately in this series, but later it will be definitely done. Now we have practice problems in binary codes. The first problem, represent the decimal number 8620 in BCD XS3 code, 2421 code and as a binary number. What is binary number? They are asking you to convert decimal to binary. This is binary number. So let's start. Let's take the decimal value 0 to 9. Let's take the BCD code. What is 8 here? 1 000, 6 is 0110, 2 is 0010, 0 is 4 zeros together. I am giving you the representation of a particular digit in that particular row column intersection so that it will give you clarity. So this is how you will be writing an answer with all the 16 digits together. What about the XS3 representation? What is 8? 1011. What is 6? 1001. What is 2? 0101. And what is 0? 0011. So the XS3 can be written as 1011, 1001, 0101, 0011. What about 2421 code? 8 is written as 1110, 6 is written as 1100, 2 is written as 0010 and 0 is written as 4 zeros together. So now 2421 code will be 1110, 1100, 0010 and 4 zeros together. How do we convert a decimal number to binary number? The only way is to divide it by 2. 8620 when divided by 2, the quotient is 4310 and the remainder is 0. When 4310 is divided by 2, the quotient is 2155 and the remainder is 0. 2155 when divided by 2, it will give 1077 as quotient and 1 as remainder. 1077 by 2 will give 538 as quotient and 1 as remainder. 538 divided by 2 will give 269 as quotient and remainder as 0. 269 by 2 will give 134 as the quotient and 1 as remainder. 134 divided by 2 will give 67 as the quotient and 0 as the remainder. 67 by 2 will give 33 as the quotient and 1 as remainder. 33 by 2 will give 16 as the quotient and 1 as remainder. 16 by 2 will give 8 as the quotient and 0 as the remainder. 8 by 2 will give 4 as the quotient and 0 as the remainder. 4 by 2 will give 2 as the quotient and 0 as the remainder. Again 2 ones are 2. So 1 will be the quotient and 0 will be the remainder. Now you have to write this in reverse order. So the binary equivalent will be 1 0 0 0 0. There should be 4 zeros here. Then you have 11 0 1 0 1 1 0. So there are 14 bits totally. So I have divided it as 7 bits and 7 bits. For readability purpose I have done that. The binary number will be this value. The next problem. For the weighted codes 3321 and 443 2. For the decimal digits. Determine all possible tables so that the 9's complement of each decimal digit is obtained by changing 1s to 0s and 0s to 1s. When you want for decimal digit, we should remember this. 0 and 9 should be complementing, 1 and 8 should be complementing, 2 and 7 should be complementing, 3 and 6 should be complementing, 4 and 5 should be complementing. This rule should be in your mind when they say the 9's complement has to be obtained. Let's take the decimal value. First we have 3321 code. How many numbers does it have? 3 plus 3 plus 2 plus 1. It is 9 numbers. So let's take the 3321 code. How do we represent 0 in this code? We will represent it with 4 zeros and obviously 9 will be with 4 number of 1s. 3 plus 3 is 6, 6 plus 2 is 8, 8 plus 1 is 9. How do we represent 1? The only way to represent 1 is this way. Then how will you represent 8? Just the complement. Put a 0 here and change everything to 1. 3 plus 3 is 6, 6 plus 2 is 8. This is the only way you can write. What about 2? The only way to represent 2 in this weighted code is using this format. What about the complement? 1, 1, 0, 1 will give you 7. 3 plus 3 is 6, 6 plus 1 is 7. They are asking you to find all the possible tables. What does the question mean? When we saw 2421, I told you there is also a possibility to write 1 plus 4 as 5, 2 plus 2 plus 1 as 5. Similarly, for 7, we can represent 4, 2, 1 as 7 or 2, 4 and 1 as 7. So they are asking what possible tables you can bring from 3, 3, 2, 1. So this is one possibility. Where the change occurs is from 3 to 6 the change will be occurring, because when you start 3 you can either start from here or from here or even from here. Let's start the 3, 3, 2, 1 table now. Let's take the first table. First I am going to start with 2 and 1 as 3. This is going to be 0, 0. Now 3 and 6 should be complementing. So this is 6. The top 3 rows and the bottom 3 rows will not be changing. The change is going to happen only in the middle 4 rows. How can I represent 4 and 5? I can represent it as 3 plus 1 and 5 can be represented as 3 plus 2. The next table. Don't change 3. Keep it as it is. 3 and 6 are not going to change. Now we are going to change only 4 and 5. How does this happen? 3 plus 1 is 4. There is also another 3 here. So the representation can be 3 plus 1 is 4 and this 3 plus 2 can give you 5. Is this a different representation? So I have two representations in 3. This makes a count of 2 tables. See, for 4 and 5, 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0. This is complementing. Similarly, in this table, 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0. It is complementing still. Now we will go to the next table. There is another possibility of writing 3. Having 1 here and remaining places you can have 0. For 6, you can have 3 plus 2 plus 1 as 6 and 0 in the first place. This is also self-complementing. So for the next 3, I have 2 combinations of 4 and 5. This 4 and 5 is not going to change. The first table is 4. 3 plus 1 and 3 plus 2. The same values, but here 3 is changing. The next table will have 3 and 6 as it is. And the next combo of 4 and 5. 0, 1, 0, 1. 1, 0, 1, 0. 4 tables as of now. The next 3 can be written using the second column. The remaining places can be 0. So here another 3 is possible and 4, 5 combos are possible, and this will also give 2 tables. So 1, 3 is written using 0, 0, 1, 1. And 1, 3 is written using 1, 0, 0. The other 3 is written using 0, 1, 0, 0. So for 1, 3 I have 2 values of 4 and 5. For this 3 I have 2 values of 4 and 5. For this 3 I have 2 values of 4 and 5. Now this will be 1, 0, 1, 1. 3 plus 2 plus 1, which is equal to 6. Now the first 4 and 5 values will come here. And for the 6th table, the 3 and 6 positions will stay as it is. There is no change. And the second combination of 4 and 5 will come here. So 4 and 5 are changing interchangeably. 1 combination, 2 combination. Similarly 1 and 2, 1 and 2. This is changing. But here 3's are same, 3's are same and 3's are same. So that's what I splitted and wrote here. It is giving 6 tables altogether. Now let's take the 4, 4, 3 minus 2 code. You have to see 0 and 9, 1 and 8, 2 and 7, 3 and 6, 4 and 5. In that you will have no changes in 0 and 9, 1 and 8, 3 and 6. These 3 will remain steady. So 0 can be written as 4 zeros. What is 4 plus 4? It is 8. 8 plus 3 is 11. 11 minus 2 is 9. So all the places will be 1 here. Make sure you are following this rule. What about 1? The only way to form 1 is 3 minus 2. So just have 1 here in both the places. So 3 minus 2 will give you 1 and have 2 zeros here. Now just reverse this. 1, 1, 0, 0. What is 4 plus 4? This is 8. So the only way to have 8 is also this one. Now what about 3 and 6? Why am I not touching 2 here is I can pick 4 minus 2 from here or from the first and the last. Let's go to 3. 3 has the only possibility of having 1 here and 6 has the only possibility of having 0 in the third position. Rest of the places 4 plus 4 is 8, 8 minus 2 is 6. So these 6 rows will have no change. We are getting into the table. 2 can be written as 4 minus 2. We'll have zeros here. Then place 1 in the respective 0th place and 0 in respect to 1's place. You will have 4 plus 3 which is equal to 7. So 4 plus 3 and 4 minus 2. So let's take the other table. We'll have the same positions here. Now we will do for 4. How will we do 4 here? We can place 1 in the first position and make everything 0. The complement will be 0 here and 1 everywhere. 4 plus 3 is 7. 7 minus 2 is 5. The other way of writing this is placing 1 in the second bit. The rest of the bits will be 0. Now 5 can be written as 1, 0, 1, 1. The complementing part. 4 plus 3 is 7. 7 minus 2 is 5. So you are interchanging 4 and 5 here. 2, 7 has two forms of 4 and 5. Now the third table. You can also write 2 in the other way. You can manipulate this 4 and this minus 2 for 2 and 4 and 3 for 7. So there is an other way of writing 2 and 7 for which you can have 4, 5 combinations again. So let's have 1, 0, 0, 1. This is 0, 1, 1, 0. Again we will repeat the same. Now for 4 and 5, I will use the first table. 1 triple 0, 0 triple 1 and the second combo 0 1 0 0, 1 0 1 1. So this will also have 7 and 4 minus 2 in this way. So for 1, 2, 7 you are having 2 tables. For another 2, 7 you are having 2 tables here. So altogether there are 4 tables. Because of these 4 rows you are having 6 tables here. And because of these 1, 2, 3, 4 rows here, you are having 4 tables. Altogether, 3, 3, 2, 1 will have 6 different tables. 4, 4, 3 minus 2 will have 4 different tables. This is just a way to give you practice of how to work with weighted codes. The next question. A binary code uses 10 bits to represent each of the 10 decimal digits. Each digit is assigned a code of 9 zeros and a 1. The code for digit 6 is given. Determine the binary code for the remaining decimal digits. Now let's take the decimal number and the code 6 is 000, 1, 000, 000. So there are 9 zeros along with the 1. We have 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 decimal digits are represented by 10 bits. And they say every digit is assigned a code of 9 zeros and 1 in the binary code. The digit has only 1 in this place. Obviously, this digit should be 6. So the code can be written in this way 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So directly in the column which has 6, they have placed a 1. So this is how we have to interpret from the question. So if 6 is going to have 1 directly, then you will have other numbers having 1 straight to that number. If you take 0, only 0 will have 1. The remaining will be zeros here. So here you can have 9 zeros together. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the 1 is this number that is denoting 0. If you take 1, only this position will be 1. If we take 2, only this will be 1. If we take 3, only this will be 1. For 4, it is 1. For 5, it is 1. In this order, we are having 1 in the 6th place as per the given question. For 7, it is here. For 8, it is here. For 9, it is here. In every row, there are 9 zeros and 1 bit. Since 1 is present in only one place, the remaining has zeros. We conclude that the respective number's position is alone taking 1. The next practice problem. Obtain the weighted binary code for the base 12 digits using weights of 5, 4, 2, 1. How much is 5, 4, 2, 1? 5 plus 4 plus 2 plus 1. 9 plus 2, 11 plus 1, which is equal to 12. So let's take base 12 digits. So from 0 till 11 it is there. Let's have 5, 4, 2, 1 here. How will you represent 0? 0, 0, 0, 0, it's here. How will you represent 1? 0, 0, 0, 1. 2 is represented in this way. 3 is represented in this way. 4 is represented in this way. How will you write 5? Let's take the same order. 4 plus 1 is 5. Then 4 plus 2 is 6. 4 plus 2 plus 1 is 7. 8 can be written as 5 plus 2 plus 1, which is equal to 8. This is 5 plus 2 plus 1, that is equal to 8. What is 9? 5 and 4 will give you 9. What is 10? 5 plus 4 plus 1 will give you 10. So this is 5 plus 4 plus 1, that gives you 10. What about 11? 5 plus 4 plus 2 will give you 11. 9 plus 2 will give you 11. So this 9 is 5 plus 4, which is equal to 9. So this is one way of getting the weighted code. There is also another way. I can have 5 here and triple zeros here. So this is 5, 4, 2, 1. For 6 I can have this way. For 7 I can have this way. So these three codes can have a change because there is a possibility of assigning 1 in this place. If they ask you a question, is this possible in a 5, 4, 2, 1 code to get 5? You can say yes, it is possible, because when you multiply 5 into 1 and the remaining is going to be 0, you will get 5 in decimal. So this is the weighted binary code for the base 12 digits. The final problem. Obtain a binary code to represent all base 6 digits so that the 5's complement is obtained by replacing ones by zeros and zeros by ones in the bits of the code. Here base is given as 6 and the complement is given as 5's complement, which is equal to r is equal to 6, and we have to find r minus 1's complement. What is r minus 1's complement? Whatever number is here, you have to subtract it from that. For base 11, we already worked out a problem. We have to find 10's complement. So we subtracted everything from 10. For base 10, for finding 9's complement, we subtracted everything from 9. So in the same way, we have to work it out for this. So let's take base 6 number. So r is equal to 6 here. What about r minus 1? It is 6 minus 1, which is equal to 5. How do I find the 5's complement? 5 minus 0 will give 5. 5 minus 1 will give 4. 5 minus 2 will give 3. 5 minus 3 will give 2. 5 minus 4 will give 1. 5 minus 5 will give me 0. What are the combinations possible? 0 and 5 can be a combination. 1 and 4 can be a combination. 2 and 3 can be a combination. It means when I represent 0, the complement of zeros and 1 will give me 5. When I represent 1, the complement will be giving 4. When I represent 2, the complement should give me 3. Let's take the basics numbers. Let's take for 0. When I want to represent any number by 0, it is better we start with 0, 0, 0. And obviously this 5 will have all the ones. They are asking us to obtain the code by replacing ones by zeros and zeros by ones. So only with this clue I can proceed. For 1, I have decided to have 0, 0, 1 here, and the complement part will be 1, 1, 0. You are having 0 here, you are having 1 here. So from this we can find this column is having 1. So now this is plus 1. What combination of number can give you 4? You can have 0 plus 4. You can have 1 plus 3. You can have 2 plus 2. If it is going to be 2, 2 and 1. How can I write 2? I can start this to be with 2. I can place zeros here, and obviously I can place the complement here. This is one way of writing. So the other way of writing 2, it can be 1, 0, 0 and 0, 1, 1 for 3. So this is another possibility. Is there any other binary code that we can obtain? Yes, we can obtain. Let's take 1, 3, 1. We'll have zeros here and we'll have ones here for 5. What about 1? I can represent this as 1 and this as 4. For 2, I can represent 1, 0, 1. For 3, I can represent 0, 1, 0. There are lots of possibilities. You can go with 2, 2, 1. You can go with 1, 3, 1. You can also go with 1, 1, 3. Then you can go for 3, 1, 1. What about 3, 1, 1? Let's take 0, 0, 0, 1, 1, 1. So this is 0, 1, 2, 3, 4, 5. What about 1? This is 1 and this is 4. What about 2? Yes, in any way you express, these are going to be complementing codes. So not only with 2 to 1, it can also be 1, 2, 2 and it can also be 2, 1, 2. If you end up with any of these codes, it is right only. So we have discussed more on binary codes in this video. I'll meet you in the next video. Thank you, viewers.